Let's have a look at some applications of Euler's. So exponential functions. I could rewrite Euler's formula this way. Yes, it's e to the iota theta, but of course we know that when we go round in a circle, we're at the same complex number. So I could add to the argument multiples, I suppose I should say where k is an integer there, but where we get multiples of 2 pi. There you go, that's where I've said k is an integer. So it will end up being cos theta plus I sine theta if k is an integer. In other words, e to the iota theta plus 2i k pi is the same as e to the iota theta. Again, we go around the circle, bang, we're in the same spot. And so, basically, well, that's just summarising what I just wrote, isn't it? Factorise, I get e to the I, theta plus 2 pi k equals I to theta. What it basically means is, just like trig, and no coincidence, because remember we can convert now between this exponential function into trig functions, it's also a periodic function. But interestingly, look at its period. It's not just 2 pi, it's 2i pi or 2 pi I. It has an imaginary period. And I guess if you think about an exponential function, it kind of makes sense, because if you draw an exponential function using real numbers, well, clearly there's no period there. So we'd have to use imaginary numbers to see the repetition of the shape. Trig functions then. So we can use it to prove identities. Remember these ones? We looked at it the other day. Z to the n plus 1 on z to the n we showed was always 2 cos n theta, and then the difference between the two was always 2i sine n theta. Okay, if I rearrange those, I get that 2 cos n theta is z to the power of n, which now I'm writing in exponential form, e to the I pi n plus e to the minus I pi n. So cos of n theta is a half of e to the I pi n plus e to the minus I pi n. And we can do a similar thing with the sine one, and we get the sine n theta is 1 on 2i e to the I pi n minus e to the minus I pi n. So let's use that to prove some trig identities. Well, let's start with our very basic Pythagorean trig identity. Sine squared plus cos squared is equal to 1. Sine squared plus cos squared. So if I substitute in now my relationship that we just have seen, where I'm going to convert the trig into an exponential function. So sine squared, so we'll get 1 on 2i squared, and then we're going to square e to the iota theta minus e to the minus iota theta squared, plus cos squared, so half squared, e to the iota theta plus e to the minus iota theta squared. Okay, common factor there of a quarter, and of course I squared on the bottom is -1. So when I expand out this first one, I'm going to get minus e2 iota theta plus 2 minus e to the minus 2i iota theta. Expand the second one out, and we'll see, hang on, we've got some cancelling that happens here. I've got a minus 2 iota theta and a plus e to the 2 iota theta. In fact, it's just a quarter of 4, which is 1. So we've proved sine squared plus cos squared is indeed 1. What about this one? You might recall we ended up showing this one in our earlier theory. So sine cubed theta is 3/4 sine theta minus 1/4 sine 3 theta. Well, sine cubed theta, that would be e to the iota theta minus e to the minus iota theta over 2i, or cubed. So if I cubed that, the bottom becomes minus 8i. And then on the top, I'm going to group together the different powers. So the iota thetas and the 3 iota thetas. So I have 3 lots of the e to the iota theta minus e to the minus iota theta. It's a good tongue twister, that one. Minus just 1 lot of e to the 3 iota theta plus e to the minus 3 iota theta. Well, there are our relationship for sine theta and sine 3 theta. Thus proven. What about this one? Remember the products of sum the products. So we're going to try and do our product to sum formula here. 2 sine alpha cos beta, sine of alpha plus beta plus sine of alpha minus beta. Okay, 2 sine alpha cos beta. So that'll be 2 times. There's my relationship for sine alpha, and times by 1 for cos beta. Expand that out. And remember, when we multiply, we add the powers. So I've written them as alpha plus beta and so on. Group them together. So the alpha plus beta ones I put in one fraction, the alpha minus beta ones I put in the other fraction. But have a look at what we got. E to the iota alpha plus beta minus e to the minus iota alpha plus beta over 2i. Well, that's sine of alpha plus beta. And the other one is the sine of alpha minus beta. Whilst it's a little bit fiddly, that's probably quicker than the other way of doing it. Okay, we could find the roots of complex numbers. So yet another way of finding the square root of a complex number. We can find the square roots of 1 plus root 3i. So we're saying z squared is 1 minus root 3i. Change that to exponential form. Now, that means z is minus I pi on 6. But remember, we said e to the iota theta was the same as e to the iota theta plus 2 pi k. So that will create the cycle that we need to generate all the solutions. So when I divide that plus 2 pi k by 2, we get minus I pi on 6 plus pi k. I need two solutions. They're not going to be conjugate solutions in this one, you'll notice, because I'm finding the square root of a imaginary or complex number. So k is 0 and 1. So sub in 0, sub in 1, and there's our two answers in exponential form. So if I want to convert back, I can find the two square roots of 1 minus root 3i.